Okay. Class this morning. Is the fatigue sitting in? Maybe, I don't know. Everybody looking forward to the full break. Let's pick up where we left off. Plan for this morning, everybody, is we'll certainly finish air quality here in just a little bit. Guessing that will probably take 25 to 30 minutes. We'll start with the material on chapter 5. That's quite good. We're at a good juncture here because the material on ozone, and I'll be just totally upfront with you, is quite challenging. Okay. When we first got together, I talked about understanding the science behind the issues, and this is one that I do want you to understand. Not just the fact that we're depleting ozone and there's a hole in the layer, but to go a little bit beyond that, quite a bit beyond that, to understand why it's depleting where it is, at the rate that it is. What's the chemistry behind it, right? That's, again, not an advanced level, but certainly to walk away with an understanding of the foundations as to how and why ozone is depleting. So we'll spend about 20 minutes on that this morning. I'll give you the roadmap for ozone, and then on Monday we'll come back and be able to wrap that up. So that's a really good stopping point for me in terms of full break. Remember, again, there's no class next Wednesday. And then we'll come back from full break and launch into a big discussion on. So that's where we're heading. Any questions? Any logistics before we get going? Okay. Scrolling over here to business school. Beautiful morning outside. What do you think the air quality outside is right now in Fort Worth? Good, middling, poor. How would you describe air quality? Just qualitatively, descriptively. What do you think it is outside? Moderate? Good. Anybody struggle coming in? Aside if you have any kind of asthmatic issues or whatever. Visibility? If the air quality is really good outside, right now, no matter how you look at it. Yeah, it's a nice fall morning. One of the points I want to make this morning, and I'll show you how this works, and I'll just share a personal story of mine a bit later. That even though air quality in the United States has actually improved quite dramatically over the last 2-3 decades, that is not the case for the majority of the world's population. In fact, the opposite is true. Many people, the vast majority of the world's population, are living in such highly compromised air, right, that it's impacting not just productivity, but it's impacting life expectancy dramatically. Okay, so that's one of the key take-homes from the first part this morning, right? Is this disparity again between who gets to live in good air quality and who doesn't. So this is the AQI that I mentioned on Monday. This is the air quality index. Again, there's numbers here that you don't need to remember, but I want to just give you a sense as to how this works, right? So the air quality index is a really nice, simple, and now widely used, globally used coloring system that gives the public a real sense, an immediate sense as to what the air quality is like, right? Green is good, right? Yellow is moderate, okay? Anything in orange and sort of reds and purples, air quality starts becoming highly problematic. So how is it quantified? So you can look at the AQI in two ways, right? You can take one pollutant and assign a color to it. So let's just look at the second column here, which is 8-hour ozone, right? So this is the 8-hour ozone. And remember the standard, the national standard is 0.07 parts per million. I know it says 0.075 here. This is the slightly older standard from 2015, right? So we look at all these various levels of ozone. And the bottom line is anything that is in green and yellow means your air quality meets the air quality standard. In other words, it's not compromised. Yeah, moderate is what it is. Yellow says moderate, but that is still, for all intents and purposes, relatively healthy air, okay? And the AQI assigns a score, okay, a simple rounded score depending on what your actual air quality is, right? So in other words, instead of going to the general public and saying, right now the ozone outside is 0.06187 parts per million, which to most people, including me, would be like, I don't know what that means, right? They assign a score to that, right? That may be 45, and that's green. That just simply means it's good, okay? If the ozone levels are beginning to approach the national standard, they'll assign a slightly higher score to it, maybe somewhere between 51 to 100, right? And your air quality can get worse and worse and worse. It gets worse as that score goes up to where anything above 500 is just literally off the charts. Does that make sense? Right? And you can do that for one pollutant like ozone or carbon monoxide or whatever, or you can actually average them and aggregate them across all the pollutants. Right? You can describe air quality based on all 6 criteria pollutants. The same would still hold true. If it was green, it would mean that your air quality across all 6 is good, okay? And so what we do here in the US and around the world, many countries, the vast majority of countries have adopted this air quality index, that map that I showed you at the end of class on Monday, okay, is they will ascribe air quality based on one pollutant. So the air quality in California right now may be poor based on ozone. It may be a level orange, okay? And the air quality in Beijing may be a level orange, but that may be based on particulate matter. Just depends on what you're looking at, right? But the AQI, I think, is a very, really rather unique and easily digestible way to get one's head around the air quality. So when you're driving down the highway and you see those electronic billboards and it'll say today's a level orange day, right? That's what it means. It means from an ozone perspective that the levels are somewhere between 0.07 on the new standard and 0.095, right? And that means something in terms of your respiratory system. Any questions on that, guys? Does that make sense? Yeah.
So if ozone was level 1.
That's a great question, right? So if ozone is orange and carbon monoxide green and sulfur dioxide green, how do you quantify it? They will, in terms of describing air quality, they will default to the worst one, right? So on my little iPhone here in the iWatch in the bottom right corner, I've got on my screen the temperature outside, and it pops up, right? The AQI will pop up. It'll pop up on. It'll default to whatever the worst is. Good question. Does that make sense, right? So that's the AQI. Okay. So here's the good news, right? And I think I really hope that one of the things you take away from this course is that not all things are bad, right? Human development is not all bad. Right? Air quality is not just terrible morning, noon, and night around the world. So this is the US situation. This is a sort of summary diagram to illustrate that point. It's a bit of a funky scale on the bottom here. It goes from 1970 to 2000. And then I've stretched out 2010 to 2018. I just need to update it for the last couple of years. All this does is it shows the percent change from 1970 in gross domestic product. This is the United States, right? So we've seen tremendous growth since 1970, economic development. We're traveling more, right? We're buying more cars. There's more people. We're traveling longer distances. So vehicle miles traveled has gone up. Our population in the US since 1970 has gone up 60%, right? More people. Our energy consumption has gone up, right? Our CO2 emissions have gone up, but interestingly, and I'll just point this out, and then let's just park this and leave it until we come back from fall break. Our CO2 emissions have actually leveled off and are now on the decline. Okay, and I think there's this perception that the US is just pumping out more and more and more carbon dioxide. Well, we are. We're still one of the world's biggest emitters of carbon dioxide. Okay, second biggest emitter next to China now. But we're actually starting to see some efficiencies reduce that. But my point simply is that CO2 has still gone up, right? So there's a lot of things that have gone up since 1970. And the point here, everybody, is that the red line, which is the average of all of the 6 criteria pollutants, has gone down, right? Has dropped by 3/4, 75%, 74% on the diagram, right? So all of these economic indicators and drivers have gone up in the last 50 years. And yet our air quality has improved, right? Our air quality in the United States is better now than it's ever been, for all sorts of reasons that we've mentioned, efficiencies, legislation, and so on, right? Better vehicle emissions, electric vehicles, from coal to natural gas. All of these things that I've tried to build in here has played out into this diagram. Okay, so that's the good news, right? Here in the United States. Here's an example. This is looking at, so what will be quite interesting actually is, well, we'll probably have to wait another year until all the global data is pulled together, but it's going to be interesting to see what the pandemic has done to air quality, right? Now, I'm not going to stand here and advocate that we have pandemics to improve the environment. That's a little ethically compromised, okay? But just look at what you see on the slide here. So this shows in the top, it shows the concentrations, okay? And don't worry about the scale, it's, molecules per cubic centimeter. So it shows nitrogen dioxide, right? Or a whole grouping of nitrogen oxides. So let's just say it's nitrogen dioxide. The top one is the average from March the 15th through to March 2019. So that's a 5-year average of what nitrogen dioxide looked like in the northeast of the US, right? There was March 2020 when we were just moving into the lockdown, okay? There's a difference, right? Air quality improved. Yeah, question.
Wait, on that graph?
Yeah.
Wouldn't it be hard to use it as everyone was not on the road anymore? And then I would say maybe even 8 months later, it could be just as bad as.
Oh, absolutely. No, absolutely. Right. That's the point. The point is that when you lock down, you get people off the road, you get you're generating less electricity, you got, planes aren't flying, things improve. So 100%, right? Your point's taken. My point simply is that the Earth knows how to handle this, right? And the human footprint is dramatic when it's there. Does that make sense? Yeah, and that's a good observation. Here's another one of my favorite ones. Right, this is California, and as I was trying to get this edition of the book to press, I was kind of scrambling because I literally had about a 3-week window to try and download these images and wrap my head around this. This shows California. Here's State Route 99. Some of you may have driven down that through the Central Valley. We've got Los Angeles at the bottom here, San Francisco at the top there, right? And you can just see from top left, it goes pre-shutdown, the soft shutdown, the full shutdown, and by the end of March, you can see how dramatically that air quality has improved. Now, again, we're not saying pandemics are good, right? But they are from an air quality perspective when we start reducing our emissions. So it will really be fascinating. I'll come back and circle back to this when we look at climate change and carbon and how much carbon has been reduced in 2020. They're still looking at that data, looking at the numbers. Okay, that makes sense? Okay. All right, so that's the US situation. Okay, globally, this is a very different picture, right? So this diagram here looks at global air quality. Now, this is PM 2.5, and that is the biggest challenge. That's the biggest culprit globally, is suspended particles from smoke and burning and combustion and so on, right? In the US, as we've said, ozone remains our challenge, right? Something like 125 million people live in compromised air from an ozone perspective in the US, but that pales into insignificance or much lower down on the scale when you start looking at parts of the world here in Asia, South Asia, Southeast Asia, and East Asia. The scale here is still tied into the AQI. So in the bottom left, the World Health Organization, okay, determines anything less than 10 micrograms per cubic meter. You don't need to know that number, but the blue here is healthy air according to the World Health Organization. Okay. At 12, that's where the green is. So the blue is just to give you a kind of sense of where the really good air is. Okay, the green is the next best, but according to the AQI, all the blues could just as well be greens. It's just a World Health Organization way of looking at it. So you can see the US, right, Canada, Australia, good air quality when it comes to PM 2.5. What does the gray mean, do you think? What's going on in Africa, those grayed out areas?
Data wasn't collected.
Say again?
Data wasn't collected.
Yeah, it's no data, right? So that's another challenge, even in 2020, 2021. So many parts of the world that don't have these monitors. Okay, we have an extraordinary set of air quality monitors here in the United States and in developed countries. So we're missing a lot of data. I would look at South Asia. So South Asia would be India, Pakistan, Bangladesh. East Asia would be places like Mongolia and China. Southeast Asia, we're now down into Indonesia, Borneo, Malaysia, and so on, right? That is a region that has the most compromised air. Remember our discussion on population, and I had that circle, more people living inside that circle and out of it. So clearly there's a people footprint here. Smoke and particles, PM 2.5 is the real problem, okay? This diagram here looks at the world's most polluted cities, again, just to make the point. So this is PM 2.5. I've put on the top here, as in 2019, the most polluted city in the United States was Portola in California, down in the southeastern corner of the Central Valley, right? That had average particulate matter at 16.9 micrograms per cubic meter. So that's moderate. That's the term you used earlier on. That's kind of okay, that's not great, but it's okay-ish. LA there is 12.9, Dallas is 12.3, right? Those are the most polluted cities according to the World Health Organization from suspended matter. Okay, now you look at the top 10, right? Look at these numbers here, 110, right? It's 10 times more polluted, right? That's a factor of 10 higher than DFW, okay? And you can see that six of the top 10 polluted cities are in fact not in China, right? They're in India, okay? So you've got 6 in India, 3 in Pakistan, and only Hotan in China now ranks in the top 10. In fact, Beijing doesn't make it into the top 100. There's this perception, and I showed you those images, right? There's this perception that Beijing is permanently in the smog. Yeah, it's got poor air quality, but these are some of the biggest ones. New Delhi is the most polluted city as a world capital anyway. So I experienced that. Here's just a little personal kind of story. I experienced that in November of 2017. I'll get some coffee. Has anybody been to New Delhi or that part of the world? Okay, if you ever get a chance, what a fantastic place. So I landed there on a Sunday evening, and I get driven to the hotel. It was midnight, and it was like really foggy, and I thought, wow, that's really muggy, pretty foggy. I wake up the next morning, and this is the newspaper. Right? This was the newspaper that I was reading. At the breakfast buffet. By Tuesday morning, I could barely see the breakfast buffet. Literally standing here in the hotel lobby, it was hard to see what they were serving. That's how polluted the air was, right? At that particular moment in time. But the day before, the Monday morning, they had shut down the airport for 3 days. United, America, the flights were not coming in. Some were, but international flights stopped coming in because the air was so incredibly polluted, right? This looks like a foggy morning at one of the temples. It's not. This is all suspended particles, particulate matter, PM 2.5 and PM 2.10. They ran out of masks, right? This was pre-pandemic, pre-COVID. So there were very few masks available. Okay? I just happened to be fortunate to have an amenity kit from the airline, and I had one of these face masks. I looked like a complete plot walking around. It was so heavy, it was hard to breathe, for sure. And this is what really blows me away, right? So this was the morning, I can't remember, this was Tuesday or Wednesday. I'd have a look. Does it say it on my iPhone there? No, it doesn't. I didn't capture this. Oh, no, it does. Updated Wednesday. So this was Wednesday morning. This was 3 days in. And here are the AQI values, right? So we've got PM 2.5, PM10, ozone, nitrogen dioxide, right? So there's the actual trace over the previous 48 hours. And the map on the left is the air sensors in my hotel, oh, how fortunate, was right here, okay, by this air sensor. Now remember, anything up to 100 is good air. Anything above 500 is off the charts, okay? 999, well, that was actually a meaningless measurement. It was so thick and heavy, the sensors couldn't even handle it, right, at that particular juncture. So it was absolutely extraordinary. And you can see on the left there, ozone wasn't an issue, right? Sulfur dioxide, nitrogen dioxide. Yeah, carbon monoxide was spiking a little bit because there are just so many vehicles in New Delhi. This was all suspended particulate matter. So what was going on here? So this happens pretty much every year at this time, right around September, October. So here's what happens. This is due to slash and burn agriculture. That's a topic we're going to come back and look at in chapter 7, right? So these are, you probably heard of slash and burns, okay? Shifting agriculturalists that go around and either cut down forests or cut down their crops, okay? And what they do is they harvest their crops and then they burn all the residual stubble to try and get the nutrients back into the soil. And what you're looking at here is a satellite image. So here's New Delhi over here, right? This was November 1. This was just around the time that I was there. Agra here is that's where the Taj Mahal is. Here's the foothills of the Himalayas right here. And each one of these dots is a large kind of amalgamated fire from agriculture, from the farmers. They're burning their stubble crops to try and clear the fields of all of the residual crop stalks so that they can plant their crops for the next year. It's a very traditional way of doing it there, and the government is trying desperately for the farmers to change their methods, right? They don't have heavy mechanized agricultural equipment like they do. This is not Iowa, right? This is still traditional agriculture, and you can see all that white plume blowing down here off the foothills of the Himalayas, right? So many parts of the world have such compromised air quality that it makes our polluted mornings look quite tame. Okay, well, questions? Makes sense. So the bottom line, the take home is, yeah, we have air issues here in the United States, but globally, it's a catastrophe in many parts of the world. And they estimate in places like India and Pakistan and Bangladesh, overall, over a human's lifetime, compromised air quality takes 7 years of life expectancy. It's extraordinary, right? When you really think about it. All right, let me stop there and see if there are any questions before we spend just a few minutes on this. All good. All right. Yeah.
So like according to like the pollution, would you say that like textiles and sustainability would be a main reason of the pollution, like in the gain challenges?
So I didn't catch the last part. Textiles and
Like textiles and sustainability, would you say that that's one of the main pollution factors, especially in India?
yeah, I think it is. You know, it's, and I'm no expert on India. I've just been there a couple of times, right? But the solution is extremely challenging, right? The situation is extremely challenging just given the sheer number of people. So, I mean, we know that, right? India will be the most populous country in the world. New Delhi as a city, which was just unbelievably exciting, has the same population as Australia. The city has the population of the entire country, right? And so you expand that out agriculturally, and they're using these traditional methods. And so that compromises air quality. And then you've got, you know, poor burning diesel trucks and vehicles and so on. So it's really hard for me to answer your question that, you know, is this part, it's almost certainly part of the solution. But that's one of the great challenges of a place like India. You know, I made that comment when we talked about electricity and energy, right? India has 500-600 million people that don't have access to electricity. Where are they getting their heat from? They're burning biomass, right? Problematic. Good question. I probably completely didn't answer it. Anything else? Okay, let's just spend 10 minutes here talking about another atmospheric issue. And this was, I can't tell you, I know this is well beyond before your time, but this was one of the primary environmental issues that hit the media in the 1980s, okay, sort of late 1970s to mid 1980s, besides the fantastic music of ABBA and people like that. This was front and center in the newspapers, and this was acid rain, right? You probably heard about acid rain or acid precipitation. Seems to have taken a bit of a back page story, I think, probably because of climate change, and that's a whole nother issue that we'll get to talk about. So let's just talk about acid rain briefly, and I'll probably not do this justice at all, okay? So acid rain came to the forefront of the public's attention again in the 70s and 80s when especially lakes in Sweden and Norway and Scandinavia, they started noticing that fish were dying and that the lakes themselves were dying. And then in the 1980s, in the Black Forest in Germany, they noticed that the forests were beginning to die. And it was because of the acidification of the environment. Okay, now this should take you back probably to chemistry in high school, but just as a quick reminder, this is the pH scale, my attempt at trying to draw a simplified pH scale. Okay, so we know that the pH scale is the scale that measures the acidity of a substance, right? And we go from the right-hand side where it's alkaline or the least acid to the left-hand side where it's the most acid, okay? And that's an odd scale. It goes from 0 to 14, and if you're desperately interested, I can explain why. But what it's measuring is the concentration of hydrogen ions. So hydrogen ions determine the acidity of the substance. What's even more important, everybody, is that as you move along that scale, it's not a linear scale. In other words, if you have a substance that has a pH of 4, and you're comparing that to a substance with a pH of 3, right? It's not 1 times more acidic, and then you go down to a substance of 2. That's not twice as acidic. It's 10 times every time you go down that scale. It's a log scale. So what that means is that if we go to, let's say you're dealing with pure water and it has a pH of 7, which is totally neutral, right? A substance with a pH of 6 is 10 times more acidic than a substance with a pH of 7. And a substance with a pH of 5 is 10 times 10 or 100 times more acidic than 7. 4 is 1,000 times. 3 is 10,000 times. Does that make sense, right? You're multiplying that by a factor of 10 as you go down, right? So anything from battery acid all the way up to black coffee, that's what we think of as being acidic. Make sense? So that's the pH scale. Probably remember that. Okay. So what's acid rain? We should really be talking about acid deposition, right? Because it can be, you can acidify rainfall, but you can also get these acids falling out as dry deposition, right? But most of the time, the acidification occurs in rainfall. So here's the very simple explanation of what acid rain is. It is the emission of primary pollutants, okay? And on the diagram here, I've got SO2 and NOx. So NOx, NOx, the X just refers to a variety of nitrogen oxide. It doesn't have to be nitrogen dioxide. It can be nitrous oxide or nitric oxide. So just think of it as nitrogen dioxide if you're not happy with that. So NOx and SOx, okay, is generally what we think of. Sulfur dioxides and nitrogen oxides are emitted as primary pollutants, right? From waste incinerators, power plants, vehicles, and so on. Those then go through a chemical transformation in the atmosphere to produce the secondary pollutants. Remember that infographic I showed you? Okay. And the secondary pollutants are sulfuric acid and nitric acid. So it's the acidification of the rainwater, if we're just dealing with acid rain. It's the acidification that occurs in the atmosphere through these chemical transformations, right? So sulfuric acid and nitric acid, that then falls out in the rainfall and it acidifies the environment. Does that make sense? Okay. Secondary pollutant. That's what acid rain is. So here's a diagram. I love this one. There's no particular reason why it's 2010. We could pick any particular year. The patterns come out to be the same. Let's just take a minute and look at this. This shows the hydrogen ion concentrations as expressed as a pH, right, from rainfall. And each one of these black dots is an official measuring station. And the diagram here is the average for 2010, right? So this is daily sampling of rainfall and then averaging up all of the pH. The scale on the right, you can see dark red is a pH of less than 4.1, and the green is a pH of more than 5.7. So somebody talk to me about this diagram. What do you notice about rainfall in the United States? A couple of big things here. Late like last night, and I'm not going to get through today without coffee. pH of 4.5. Okay, what do you notice, everybody? What does the rainfall map of the US look like here? There's two things I want to come off this diagram. One, what can you say about, yeah. Yeah, so there's a very sharp, obvious, and steep gradient in the pH, the acidity of rainfall. Okay, from west to east. So I want to find out why. What can you also say about the acidity of rainfall generally? Not the spatial pattern, but just the number. Wouldn't you expect to see a pH there of 7, maybe? Right? So that's a key point. Rainfall is naturally acidic. So you look at the western third of the United States, or maybe the western half. Okay, let's just look at Colorado here. Anything in dark green is a pH of 5.5 to 5.7. That's the natural pH of rainfall, the natural pH, right? The atmosphere doesn't produce Osaka water from the sky. It just doesn't. Okay? Rainfall is naturally acidic because of the gases that are in the atmosphere that naturally interact with rainfall, right? So rainfall has a pH of about 5.5 naturally, without any humans playing with it. Your point is well taken, and when you start looking east of the Mississippi, that pH is different. It's not 5.5, it's about 4.5. Okay, it's 10 times more acidic on the eastern seaboard than it is in the west. What is going on here? It's not the Mississippi River spewing out atmospheric acid. Why do you see this pattern? What explains that at a broad level across the US? Well, that would make a nice example. Yeah.
Population density.
Okay. Population density, but look at LA. San Fran, right? Yeah, something's going on. Big industry. Right? The Ohio Valley. We kind of collectively call that the industrial Northeast, right? With other things, like a little spot over here in East Texas. Now, I know it looks like there's a target there, and that's just simply because there's a recording station. Now, Texas is pretty big, right? So if you drive from wherever that is close to Tyler into Dallas, that's a 3-hour drive, and they have to interpolate the data between those locations. Right? So you get somewhat of an artificial bullseye effect, but that's real. Okay, we get higher acidity in this region over here. What happens to be located in the northeastern section of Texas? 2 or 3 of them, 4 of them actually.
What?
Coal-fired power plants. Okay. Yep. Coal-fired power plants. What do coal-fired power plants produce? Well, they produce sulfur dioxide and nitrogen dioxide, right? So it's the industrial Northeast, okay, and not just coal, but all sorts of industrial activity that acidify the rainfall on site because you're emitting the primary pollutants into the atmosphere. Those chemical transformations are taking place. Now, yeah, the rainfall isn't just suddenly turning around and falling right there, right? Because it gets moved around. But when you look at the acidification of rainfall, it's really not a West Coast problem. It's an industrial Northeast problem, which I think is quite interesting. So here's just one example of how we've actually improved sulfur dioxide. Remember that the trends, if you think back to Monday, we've seen that dramatic decrease in trends of particles. Numbers aren't critical here, it's just the image, right? 1989 to 1991, that's ambient background sulfur dioxide on the right, a decade later. Almost a decade later. It just so happened that in the early 90s, there was an amendment to the Clean Air Act. It was called the Mercury Rule, and they had to dramatically reduce the amount of mercury and sulfur dioxide emitted from coal-fired power plants. Those companies had to go in and scrub and clean out those emissions, right? So again, not all bad news. So finally, then with acid, let's just mention. So what happens? How does acid rain impact the environment? So there's 3 things here, everybody. It impacts forests, lakes and streams, and buildings. And I'm just going to fire fairly rapidly how this works, right? So forests are one of the ways, and there's 3 images here. On the left-hand side, that happens to be the Black Forest in Germany, beautiful part of the world, just down south near Munich. On the right are images from Appalachian. It's a bit grainy because it's taken from a book. Anything in gray or looks like brown or the leaves is a result of acid rain. And here's the key, right? This is not the acid rain burning the leaves. Okay, it's not like the leaves are shriveling up and bubbling because the rainfall is so acidic. It's not, right? People in the industrial Northeast aren't burning from the rainfall. Okay, so what's going on? Here's how it works. when you acidify water, when you acidify rainfall, and when you increase the acidity tenfold from 5.5 to 4.5, that acidic rainfall enters into the soil, right? And the plants will take up that water and the nutrients associated with that water, okay? And what acid does, remember, acid rainfall is hydrogen ions, okay, the concentration of hydrogen ions. What happens is that the hydrogen ions replace the nutrients in the soil, okay? We don't have to get into that. It's the way in which it's called cation exchange, and it happens on the soil particles. We can take a soils course at a 5,000 level to look at that. So basically, the rainfall and the hydrogen ions in that acid rainfall, they go into the soil and they look at a soil particle and they go, okay, you know what? I like that potassium over there, right? And I'll take that phosphorus over there and I will replace that ion, and that the nutrients get washed out of the soil. And so the nutrients that are taken up by the vegetation are concentrated in hydrogen. And therefore it shuts down, bless you, it shuts down the nutrient cycling process in the vegetation, and the vegetation begins to die. Does that make sense? It's kind of like a short circuit. So the forest, instead of just sucking up water from the soil filled with nutrients, those nutrients are now depleted because the hydrogen has come in and replaced things like potassium and phosphorus, right? So we see tree death, okay? And in the US, there's some very sensitive ecosystems. There's some sensitive forests, like the forests that occur in Appalachia and Colorado, that are particularly sensitive to acid rain. This is another map that shows forests that are sensitive, so saturated forests, but it also shows areas of surface water that are susceptible to acid rain. So basically, anything in blue on this map is water that is problematic, more acidic than not. Now, there's a really interesting, I don't know how to phrase this, environmental oxymoron here. Take a look at Texas. What's going on in Texas? Oh, incidentally, the green areas, class 1, those are just areas of special concern according to the National Park Service, the National Forest Service, the National Fish and Wildlife Service. Those are just key areas, right? But look at Texas as a whole. Does Texas have an acid rain problem when it comes to its surface waters? No, why not? We've got plenty of coal-fired power plants. I just showed you that power plant in East Texas that's pumping up sulfur dioxide. Interesting. What's going on here? Let me take a step back here. What's going on from here all the way up there? Here, there. What's going on there? What does it look like those blue waters are following? There. They're doing what? Following mountain ranges. The waters associated with lakes and reservoirs and streams in the mountain ranges are more acidic. Why? Because the mountain ranges are older mountain ranges made up of rocks that themselves are naturally acidic, right? So you've got acid soils in the first place, and any rainfall that happens to be acidic that falls on that magnifies the problem. In Texas, what is most, not all, but what is a large proportion of our rock made up of in Texas? I haven't done geology 101, 113. Maybe you get a free pass here, but if you have, when you walk around Texas, if you walk around Hill Country, San Antonio, Austin, it's what?
Clay?
Well, there's a lot of clay, but as a rock, ooh, someone said it, limestone. Yeah, we've got limestone everywhere, right? You just have to walk down West Bowie here to the bottom of the hill, down near Sandage, and where the new Hyatt Hotel is, you look up at, there's lots of limestone everywhere. So why is that important? Texas is covered with limestone. What does limestone do to the soils? Limestone does is it buffers or counterbalances the acid, right? So there's a buffering capacity in the soil. If a farmer has acidic soil and the crops aren't growing well, what does he or she do? What do you put onto an agricultural field to reduce the acidity in the soil? You put lime, right? You dump lime on it. So the fact that we have limestone soils here in Texas counterbalances the acidity of any potential rain that falls. So that's a good thing. When you're dealing with the East Coast, a lot of those soils are naturally acidic. So when you start dumping acid rain on there, it's an enormous issue, right? It sort of magnifies the problem. So here's just an image of a helicopter dumping a huge amount of lime on the lakes in Norway, and they still do this, right? And it's not that the Norwegians or the Swedes are spewing out lots of acidic rain. Most of that was coming from the UK, from England, from all the coal-fired power plants in England. And all of those sulfur and nitrogen oxides then blow across the North Sea. By the time they get to Scandinavia, they're dumping acidified rain onto the lakes, and the fish are dying. So lakes and forests, and then finally, this is the last acid rain site. It's also beginning to affect our cultural heritage. Now, this may not seem like a big deal, but I had a colleague, a friend of mine, who studied with me, and she has made her entire career, she's incredibly impressive career, looking at the dissolution of cultural monuments around the world as a result of acid rain. So on the left here, this is a 10-year difference between these two. This is a statue on one of the colleges at Oxford. Okay, and a 10-year difference because of the acidification of the environment. So acid rain is still an issue in many parts of the world. It just seems to have taken this, I don't know, step back from the forefront of the media's attention. All right, let me stop there and see if there are any questions, because I have 10 minutes, which is great. I would like to introduce concepts of ozone. So question, thoughts, and comments. Yes. Yes, it does. Good question. Does acid rain have an impact on agriculture? Absolutely, it does, because it's acidifying the soil, and then what it ultimately does is it reduces the crop yield. It puts enormous stress on the crops from a moisture standpoint. Remember, it's a really good question, because it's not the acidification of the water that's burning the crops. It's the exchanging of the ions and the fact that you've got concentration of hydrogen at the expense of nutrients like potassium and phosphorus. So that puts stress on the crops. It reduces crop yields by up to something like 30% in some areas. Yeah, good question. Yeah, another good question. How do we deal with that? How do you help those areas that are? It's really hard because it's an atmospheric problem. The problem is the atmosphere doesn't obey political boundaries, right? So if you're burning coal in England, who gets back end of that is Scandinavia, right? So you have to reduce it at the source. You have to reduce the emissions of primary pollutants. Okay, all right. So that's chapter 4, right? Air quality. And a big part of chapter 4, besides the particulates and the acid, big part of chapter 4 is ozone. Okay? So now we come back to ozone, but remember, this is a very different type of ozone. We're talking about stratospheric ozone. Here's the roadmap for stratospheric ozone. Okay. I will get to do this morning, distribution and CFCs. We've got 7 minutes and we're good. We'll get to do that. So we'll do that and finish it this morning. Okay. I then want to talk about chlorine. And that's a Nobel Prize right there. So you're probably thinking, what's that? Well, it turns out scientists were the first to articulate the impact of chlorine in destroying ozone, won the Nobel Prize for it, right? 1995. There is no Nobel Prize for environmental science. There should be, but there isn't. So they won it for chemistry, but there were 3 environmental scientists. So we'll talk a little bit about that on Monday. Then we're going to talk about the ozone hole, right, which occurs both over the North Pole, but predominantly over the South Pole. So we're going to do that. And then I want to talk about the recipe for ozone loss. Okay, cannot stress enough this point, everybody. I'm going to expect you to understand and articulate this in exam number 2. Okay, and historically, when I look at exam number 2, that's where students fall down. They go, yeah, whatever. I'm not going to learn this, and it's not easy. But once you work through it, and you can explain to me what that recipe is, you'll be in good shape. Okay, so I am going to ask you this in exam number 2. Okay. So again, just as a reminder here, we are now changing location. We're moving up into the atmosphere. So we talked about ozone in the lower atmosphere. We talked about California and Houston. It's a human-made pollutant, right? You're emitting the nitrogen oxides. You're emitting the volatile organics. Those are being converted into low-level ozone, right? The pollutant. Okay. Here we're talking about the protective ozone. It's still O3, but it occurs somewhere in the region of 12 to 15 miles up in the layer that we call the stratosphere. All right. Important diagram here. This shows the vertical distribution of ozone, right? So if you were to take the average, if you were to take a whole bunch of weather balloons and let them go up into the atmosphere, and you were measuring the concentration of ozone, right? Not stratospheric or tropospheric, just ozone. And you were to let those weather balloons go up across the globe, and you were to take the average of that, this is what the distribution would look like, okay? So we've got altitude in miles and kilometers. I know most of you will focus on miles, but I still sort of default to kilometers. So that's altitude on the left there. And we're expressing ozone here just in terms of the amount of pressure that's being exerted by the ozone. Don't worry about that. It could be pressure, it could be concentration or anything, right? So the scale on the bottom is not the critical part. It's just giving you an idea of how much ozone there is. So what you have here from the surface going up is ozone at the surface is generally high, and then it decreases as you go up through the first 1, 2, 3 miles, right? That little peak at the bottom, that is the low-level tropospheric human-made pollutant that we've talked about already. Okay, so that's chapter 4. That's what we're living with here in the US. Low-level tropospheric ozone. It accounts for about 10% of all the ozone in the atmosphere, okay? And it is a pollutant. So then you go up vertically and ozone just kind of wiggles and woggles a little bit. And then you get to this layer that starts at about 10 miles up. It varies depending on where you are on the planet. It generally starts at about 10 miles. And ozone concentrations then go up dramatically. And they peak here at about, 13, 14, 15 miles up, something like that, right? Does everybody see that? There's a ginormous peak. The concentration goes up, and then it begins to decline again. That is the so-called ozone layer in the stratosphere, right? And let me just kind of dispel one important myth here. A lot of us, and I think it's an easy way to think about it, we think of the ozone layer as this shield, right, that protects us, as a sort of thin layer or shield. Yes, it protects us, and I'll explain why, but it's actually more, think of it more of just a gas that's distributed throughout the stratospheric ozone layer. It happens to be highly concentrated at about 12 to 15 miles, right? So it's not like there is one line here that comes all the way straight back and then ozone goes to zero. It's not a lid that's sitting on top of the atmosphere. It's a gas that is distributed throughout the stratosphere. It just happens to be highly concentrated at about 12 to 15 miles. About 90% of all the ozone in our atmosphere, and that's the good ozone, right? That's the good up high. It's the ozone that protects us from harmful ultraviolet radiation. Question on that. So that shows the average vertical distribution of ozone in the atmosphere. Low-level tropospheric human-made chapter 4, high concentrations of stratospheric ozone into chapter 5. Well, good. All right. So let me end here. What do we got? 3 minutes. Good. Key point here. Ozone in the stratosphere is formed and destroyed naturally. Right? That's the starting point. Monday, we're going to come back and look at CFCs and other things. Right? So this cycle describes very simply, I hope, how ozone is formed and destroyed in the stratosphere. So what we've got here, everybody, is these individual O's or oxygen atoms. O2 is an oxygen molecule like you and I breathe. O3 is ozone, right? How does this work? So we've got low concentrations of O2 in the stratosphere, right? It's not nearly as highly concentrated at the surface. So we've got O2 in the stratosphere. Sunlight strikes those O2s and splits them apart into individual oxygen atoms. And those individual oxygen atoms then find an O2 and form an O3. That's what you see here in step 1 and step 2. Does that make sense? Right? So sunlight splits apart O2, releases the individual oxygens, and the oxygens now go and find an O2 to form an O3. That happens naturally, right? It happens because of the high energy ultraviolet radiation from the sun that is splitting apart the oxygens. Please throw your hands up if that doesn't make sense. Right? Natural destruction of ozone by sunlight, okay? So then what happens? At the same time, in an ongoing process, the sun's rays will strike the O3 and break apart the oxygen, leaving behind the O2 and the individual oxygen atoms. Right? That's step 4. That is a continual process of creation and destruction going on right above our heads all the time. Sunlight splitting oxygens, releasing the oxygen atoms, joining up with O2 to form O3, sunlight striking the O3, disassociating it into O's and O2s. Right? Does that make sense? That ongoing process of creation and destruction over time has led to a buildup of stratospheric ozone, right, over millennia, to the current concentrations that we have in the stratosphere. Make sense? Okay, that's a good stopping point. We have no choice. Stopping point. We're going to come back and then put that into context. There. All right, thanks everyone.